Can a moon vanish? It turns out it is possible. In the early days of astronomy, the Saturnian moon Iapetus routinely appeared to vanish from sight entirely. Some days it was there and the next it was gone. This was the ultimate magician's trick, but as we figured out how it was done, Iapetus's mysteries only grew deeper. That is because Iapetus is a place of profound contrast, one half plunged into near absolute darkness, and the other half gleaming with the brilliance of reflective ice. Around its equator, a colossal mountain range, a stony girdle wrapped precisely around its equator, whose origins defy explanation. Why does this moon present such a dramatic two-faced characteristic? What cataclysmic event or slow, inexorable process could have sculpted a mountain chain taller than Mount Everest in a place that defies explanation? And what secrets does this distant world hold about the turbulent youth of our solar system? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we journey to Iapetus, Saturn's third largest moon, and arguably its most enigmatic. Our story begins with the keen eye of Giovanni Domenico Cassini. In 1671, using the refracting telescopes of the Paris Observatory, Cassini spotted a new point of light orbiting the ringed giant. But this new moon behaved strangely. When it was on the western side of Saturn in its orbit, it was reasonably visible. But as it traveled to the eastern side, it seemed to vanish, becoming incredibly faint, often disappearing entirely from view in those telescopes. Reflecting on his observations, Cassini remarked that sometimes after having begun to disappear with the 32-foot telescope, it has been sought in vain the next day with one of 45. Cassini concluded that this moon must have one hemisphere that is significantly darker than the other, and it must be tidally locked to Saturn, always keeping the same face towards its planet, just as our own moon does towards Earth. This meant that as Iapetus orbits Saturn, it alternates in presenting its bright face and its dark face towards Earth. When the bright side faced us, on the western side of its orbit from our perspective, it was visible. When the dark side faced us, on the eastern side, it faded from view. It was an astonishing observation for the 17th century and marked the first surface property ever detected on a planetary moon outside the Earth-Moon system. Cassini named the four moons he discovered Sidera Laodicea, or the Star of Louis, in honor of King Louis XIV, but these names didn't stick. Later, John Herschel suggested names from the Titans, brothers and sisters of Saturn in mythology. Iapetus, the father of Atlas and Prometheus, and by extension, father of Prometheus's creations, mankind became the moniker for this peculiar world. For centuries, Iapetus remained little more than a point of light exhibiting this bizarre brightness variation. Even the Voyager probes, which revolutionized our understanding of the outer solar system in the late 1970s and early 1980s, only managed distant flybys. Voyager 1 captured images showing the dark brightness difference, confirming Cassini's deduction, but the resolution wasn't high enough to reveal the intricate details. Voyager 2 fared slightly better, passing closer and giving us our first tantalizing glimpse of another astonishing feature, a hint of the massive ridge near the equator. But the full picture, the breathtaking weirdness of Iapetus, would have to wait for the arrival of a dedicated Saturn explorer. Enter the Cassini spacecraft, named, fittingly, after the moon's discoverer. Arriving at Saturn in 2004, the Cassini mission would spend 13 years unveiling the secrets of the ringed planet and its diverse family of moons, and Iapetus was high on its list of targets. Cassini's observations, particularly a close, targeted flyby in September 2007, that brought the probe within just 1,640 kilometers of the surface of Iapetus, transformed the moon from a distant glint into a complex world we could finally study. Iapetus is a moon with a low density, just 1.2 times the density of water, suggesting that it's composed of up to 75% water ice. Its shape is not perfectly spherical, partially due to the equatorial ridge, giving it that distinctive, oblate, walnut-like appearance. It likely doesn't possess a subsurface ocean like Enceladus or Europa, as there's no evidence of recent geological activity or the tidal heating needed to maintain liquid water deep beneath its icy shell. Its surface is ancient, cold, and heavily cratered, particularly in the bright regions of Roncevaux Terra, testifying to billions of years of bombardment. Its orbit is also unusual. Iapetus orbits much farther out than other Saturnian moons, at an average distance of about 3.5 million kilometers, more than twice the distance of the next major moon, Titan. This large distance means it takes 79.3 Earth days to complete one orbit around Saturn. Crucially, its orbit is also slightly inclined, tilted by about 15 degrees relative to Saturn's equatorial plane, where most other major moons orbit. This distance means Iapetus is less affected by Saturn's magnetosphere and the intense radiation belts closer to the planet. Its orbital inclination might be a clue to its formation or early migration history, possibly indicating it didn't form with the same equatorial disk as Saturn's closer, regular moons. But let's turn to the aspect of Iapetus that makes it so fascinating to look at: its surface. Iapetus is cleanly divided into two distinct regions. The leading hemisphere, the side that faces forward as Iapetus orbits Saturn, is incredibly dark. This region is known as Cassini Regio, and it covers about 40% of Iapetus' surface. Its albedo, the measure of how much light it reflects, is extremely low, somewhere between 0.03 and 0.05. That's as dark as asphalt or coal dust. It absorbs almost all the light that falls on it. In stark contrast, the trailing hemisphere, the side facing away from the direction of orbit along with the poles, is incredibly bright. This region, encompassing Roncevaux Terra to the north and Saragossa Terra to the south, boasts an albedo of 0.5 to 0.6, as bright as freshly fallen snow or brilliant water ice. This almost tenfold difference in albedo is the greatest interhemispheric albedo contrast that we know of in the solar system. Imagine seeing this world up close, one side a deep reddish brown or black, the other a dazzling white. In some areas, particularly near the equator, the boundary between those halves can appear remarkably sharp, as if painted on. In other areas, especially at higher latitudes, the transition is more gradual, with bright rayed craters splattered across the dark terrain, and dark streaks dusting the bright terrain, like splashes of mud on snow. This image from Cassini vividly shows this contrast. It is a world literally split down the middle. So, what causes this yin-yang appearance? For a long time, the leading theory proposed an internal origin, perhaps some form of dark, cryovolcanic material erupting from Iapetus' interior and coating one side. A paper reviewing the Voyager data from Bradford Smith and his colleagues in 1981 argued for this theory, identifying this ring shape as a crater partially flooded with dark, eruptive material as supporting evidence. However, Cassini's radar and imaging data revealed that the dark material forms a relatively thin layer, perhaps only tens of centimeters to a meter thick in most places. Furthermore, impact craters within Cassini Regio often excavate bright, icy material from underneath, punching through the dark veneer. This strongly suggested the dark stuff wasn't welling up from below, but was being deposited from above. A paper in 1982 made spectrophotometric observations of the dark leading surface and found that the composition of material was carbonaceous, similar to that of the Murchison C2 meteorite, which fell to Earth during a shower in 1969. To explain this finding, the authors looked to potential culprits close to Iapetus within the Saturn system. The prime suspect? Dust from Saturn's outer, irregular moon, Phoebe. Phoebe is a relatively large, dark moon captured by Saturn's gravity, orbiting the planet in the wrong direction, a retrograde orbit at a great distance. Over billions of years, impacts on Phoebe and other small, dark, retrograde moons have kicked up a vast, tenuous ring of dark dust particles. The sun's radiation exerts pressure on these dust particles, causing what is known as the Poynting-Robertson effect. As a result, this dust spirals inwards towards Saturn, also moving in a retrograde direction. Now, back to Iapetus. It orbits Saturn in a prograde direction, the same direction as Saturn's rotation and most other moons, but its orbit is significantly further out than the main rings and closer moons. As it journeys around Saturn, its leading hemisphere essentially plows head-on into this incoming stream of retrograde dark particles originating largely from the Phoebe group. It's like driving through a swarm of insects. They mostly splatter on your front windshield. The trailing hemisphere, shielded by the moon itself, collects far less of this dark material. But deposition alone doesn't fully explain the intensity of darkness we see on the leading side of Iapetus, or the complexity of the border between dark and bright. This is where thermal segregation and water ice sublimation come into play. The dark material deposited on the leading hemisphere absorbs more sunlight than the surrounding bright ice. This causes the surface temperature to rise slightly. Iapetus is incredibly cold, but even a small temperature increase is enough to cause the volatile water ice to sublimate, turning directly from solid ice into water vapor gas. This sublimating water vapor doesn't just disappear. Because Iapetus rotates very slowly, its day is about 79 Earth days long, matching its orbital period, daytime temperatures are higher, and the ice has plenty of time to sublimate away from the warmer, dark areas. In fact, sublimation on Iapetus is so fast, if its surface were pure ice, we would see over 100 meters of ice lost to sublimation in a billion years, but that's still faster than any Saturnian satellite. But where does the ice go? It preferentially recondenses and freezes onto the coldest available surfaces. These are the already bright, icy regions on the trailing hemisphere and near the poles, which reflect more sunlight and stay cooler. Scientists suggest that due to its negligible atmosphere, sublimating molecules follow ballistic trajectories, jumping impressive distances to the trailing hemisphere in the style of a missile. This creates a runaway positive feedback loop. Dark areas get slightly warmer, lose their ice, become even darker as the underlying dark dust concentrates. They absorb more heat and sublimate more ice. Bright areas stay cold, collect migrating frost, becoming even brighter, reflect more sunlight, stay even colder, and collect more frost. Over millions and billions of years, this process has dramatically sharpened the boundary between the dark leading hemisphere and the bright trailing hemisphere, leading to the extreme contrast we see today. So, the Great Dichotomy seems to be a combination of external pollution from retrograde moons and an internal sorting mechanism driven by sunlight and ice sublimation. A truly remarkable example of planetary processes at work. But the two-tone coloration is only part of Iapetus' strangeness. As Voyager 2 hinted at, and Cassini confirmed in stunning detail, Iapetus possesses another unique feature in the known solar system, a colossal equatorial ridge. This ridge is effectively a wall of mountains, stretching for around 1,600 kilometers, at least halfway around the moon's circumference. On average, it is about 200 kilometers wide at the base and reaches towering heights of up to 20 kilometers above the surrounding terrain. That's significantly taller than Mount Everest. And the most baffling part, it follows the equator almost perfectly, primarily confined within the dark Cassini Regio, although more equatorial mountains identified by Voyager on the trailing hemisphere could be a continuation of this structure. In images like this one, taken by Cassini during its close flyby, the scale is breathtaking. It gives Iapetus a distinct walnut shape. What could have possibly formed this belt of mountains? This is one of the biggest ongoing mysteries of Iapetus. Several hypotheses have been proposed, each with its own strengths and weaknesses. One leading idea suggests the ridge is a relic of a much faster spinning past. Recent models have suggested that early in its history, shortly after formation, Iapetus might have been rotating much more rapidly, perhaps completing a rotation in around 16 hours. This rapid spin would have increased oblateness, causing the moon's equatorial regions to bulge outwards due to a centrifugal force, while the moon was still young and relatively plastic or partially molten. As Iapetus cooled and solidified, this equatorial bulge froze in place. Later, gravitational interactions with Saturn slowed the moon's rotation down over millions of years until it became tidally locked, rotating only once per orbit, or 79 days. As it slowed, the centrifugal force supporting the bulge diminished, and the now solid crust couldn't fully relax back into a sphere. The material essentially slumped downwards, piling up near the equator to form the massive ridge we see today. This theory fits well with the ridge's equatorial location and its ancient, heavily cratered appearance, suggesting it formed very early on. However, it requires Iapetus to have spun incredibly fast, possibly close to its structural breakup speed, and to have solidified while maintaining that bulge. Another intriguing hypothesis proposes that the ridge is the result of material falling onto Iapetus from an external source, specifically the collapse of a sub-satellite or a ring system that once orbited Iapetus itself. If Iapetus possessed a debris ring early in its history, perhaps sourced from a captured body or a large impact, this material would naturally orbit above its equator. If this ring became unstable, or if Iapetus migrated slightly in its orbit, the ring material may have been pushed just beyond the Roche limit, which is the point at which the tidal effects of a large body overwhelm the internal gravity of a smaller one. This may have caused the ring material to slowly rain down onto the surface of Iapetus, piling up preferentially along the equator. This could potentially explain why the ridge seems most prominent on the dark leading hemisphere if the ring material itself was dark, or its deposition coincided with the influx of dark dust from Phoebe. Some models suggest that even a small moonlet breaking up within Iapetus' Roche limit could provide enough material. While elegant in explaining the location, the exact mechanisms for forming and then collapsing such a ring are still debated. Other theories, such as tectonic processes or convective upwelling from the interior, struggle to explain why the activity would be so narrowly confined to the equator over such a vast distance. A giant impact is also unlikely to produce a long, linear, and perfectly equatorial feature. Cassini's detailed images show the ridge is heavily cratered, confirming its ancient origins. It appears to be structurally composed of icy, crusty material. Some sections show evidence of landslides and collapse features. Whatever the process, it must have happened very early in Iapetus' history, perhaps within the first few 100 million years of the solar system's formation. The ridge stands as a monumental memento of Iapetus' dynamic youth, a frozen record of processes we are still striving to understand. So, what do we know about Iapetus? More than we used to, but less than we'd like. The Cassini mission fundamentally changed our perception of this fascinating moon. Its close flyby provided the data that solidified the exogenic dust and sublimation theory for the planet's two faces. It gave us astonishing, high-resolution views of the equatorial ridge, allowing detailed study of its structure and morphology, even if its origin remains debated. Cassini measured Iapetus' shape, gravity field, and surface composition with unprecedented accuracy. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light it was for centuries. And yet, there are still so many mysteries. What is the true origin of Iapetus' ridge? What is the dark material of Iapetus' mysterious face actually composed of, beyond something simply carbonaceous? Unless we go there, it will be difficult to know for sure. No missions are currently planned to sample or even circle this perplexing place, so for now, we remain in the dark. Which feels appropriate. After all, as I said at the beginning, Iapetus was once the ultimate vanishing act, and a magician never reveals his secrets. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on Iapetus. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time. soon.